Hello, everyone. Hi. Thank you so much for joining us this evening for 60 Minutes in Space. This is our monthly sort of 60-minute download of what's new in space news. Tonight, our curator of space science, Dr. Chun Yu, will be presenting, and then we'll have a brief question and answer following the presentation. So again, thank you for being here, and here's Dr. Chun Yu.
All right, thank you very much, Charlotte. Welcome everyone to 60 Minutes in Space, and this is actually the first one that I've done since February 2020 in the Planetarium. So it's kind of interesting to be back. How many of you are new to 60 Minutes? Raise your hands. Okay, so about half the audience. Welcome, as Charlotte said. We do a monthly program, although that's not quite true because I don't think we have one set for November nor December because it's the last Wednesday of the month, and so the next 2 months are pretty complicated by the holidays. Unfortunately, we won't see you until 2023. But what we do is cover to some degree greater depth about some of these more prominent space science news that you might have even seen or heard yourself on the internet or in a magazine article from the last month. And typically, as an astronomer, I like to cover things outside of our solar system, so stars and galaxies, and we'll be doing a lot of that. But I'll also turn my attention to something that happened inside of our solar system that you probably heard about as well. We do have other guest speakers that come and do these, and they tend to have a wide range of expertises. And so depending on which speaker and when you come back, you might get more coverage about Mars or things happening in our solar system or astrobiology. But tonight, we're going to be doing a lot about stars and galaxies and showing a lot of pretty pictures. So with that, what I'm gonna do is I'm gonna actually talk from the top just because it's kind of difficult to see down here. So we'll get started. All right, so the first topic, or actually first set of topics that I'll be covering will be about the James Webb Space Telescope. And as many of you are aware of, the James Webb was launched last December on Christmas Day. And it's been returning a lot of great results that have been appearing in the news. And one really fun picture that was released this past month is of this galaxy, IC 5332. And this is a spiral galaxy. And this is not a James Webb Space Telescope picture. This is actually from the Hubble Space Telescope. And so this galaxy is a spiral galaxy. And you can see a bright core to the center of the galaxy and has these nice spiral arms that make it look like a pinwheel. And our Milky Way galaxy is pretty similar to this, although the Milky Way is what we call a barred spiral, not one of these types of spirals. And what you notice is that along the spiral arms, you see lots of dark clouds. And those are dark molecular gas clouds. These dark regions are not places where you're missing stars. These are regions that are so dense that starlight can't poke through to us. So you see lots of these dark clouds that line or outline the spiral arms. And then you also see these bright clusters. So notice that there are these bright bluish star clusters. There's also this kind of red grouping of stars. And these are regions where young stars have been born. And so the reason why this glows red is because the ionizing radiation, ultraviolet radiation from massive young stars are lighting up the hydrogen gas in this region. And it's giving us that reddish glow. And once those stars basically burn out or destroy the molecular clouds that they're born in, they expose the clusters that are then revealed. And so you have these bright little clusters of, we can call them open clusters, but they're bluish because they're filled with massive young stars, which tend to be bluer than the older stars that make up the kind of the orange part of the bulge, that central bulge in this galaxy. All right, so let's look at what this galaxy looks like from James Webb. And so you can see this looks really, really different. And what James Webb does is, instead of looking in optical light, so Hubble is looking in the visible wavelengths that our eyes are sensitive to, it's looking in this case, the mid-infrared. And in order to do that, it uses a detector that's been cooled to about 6 or 7 degrees above absolute zero. And so it's looking at emission and in order to be sensitive to this, the electronics, the detector has to be cooled so that there's no heat from the detector swamping the very small amounts of radiation that's coming in from this galaxy. And so what we're seeing is actually radiation that's coming from the gas clouds in this galaxy. So whereas if you look here, you can sort of make out the gas clouds, like I said earlier, that sort of look like these dark clouds. But if you look here, you can see that there's a whole structure to these clouds. I mean, it's almost like a skeleton that's buried underneath all the stars and gas that you can't see. But if you look, here's a structure. Look at this structure here. It looks like kind of a hook with a handle, and you can see that same structure showing up in the mid-infrared. But in the mid-infrared, and this is why the James Webb was built and launched into space, was because a lot of these infrared wavelengths are not accessible from the ground. And you can't, you can see some infrared wavelengths from ground-based telescopes, but you really have to get into space to be able to see what we have here. And you can even notice that some of these bright clusters, like that one, sort of show up. You can see that there's a bright grouping of stars there that corresponds to that cluster, but there's this cluster over here that also looks really bright in the infrared. It doesn't really look like anything in the optical. And so you can tell just by comparing these two images that there's a lot of stars, a lot of clusters, star formation that's hidden by gas and dust in this galaxy. And you really have to go into the mid-infrared to be able to just pull out these features. All right, let's go on to the next image. And this is one that many of you are familiar with. These are the famous pillars of creation in M16 in the Eagle Nebula. And this is a Hubble Space Telescope image. And so our very first image from Hubble of this feature came out in, I think, 1994, 1995. This image was an updated image from Hubble taken in 2014. And what we're seeing is, again, one of these gas clouds that we've been talking about, but instead of looking at them from far away, we're looking at them from much, much closer. This is inside our own galaxy. And this is a region where there are a lot of stars that are being born. And in fact, way up here, so up towards the top of our dome, there, if you can imagine, if you could extend this image, there would be a group of massive stars. And these massive stars are relatively young, and they pump out huge amounts of ultraviolet photons, ultraviolet radiation, and they also blast out these very powerful stellar winds. And what happens is the gas environment in this whole region is being excavated away by the radiation and by the winds. And so the reason why you have these spectacular looking shapes is because they're being etched away. So there used to be gas all around here, but the winds and the radiation have basically blown apart the gas cloud. And so what you have left are these fingers. And the reason these fingers have persisted is because there's probably very dense clumps of gas at the ends here. And they've basically helped to shield the rest of the cloud. And so this whole region is filled with relatively young stars. And again, let's take a look at what this looks like in the mid-infrared when we go to the James Webb. And so here you're again seeing the same structures, but look at how transparent this part of the cloud is, and even all around. So basically there's huge amounts of gas that is blocking the starlight. So there are lots of stars in the background, but we can't see them until we go into the mid-infrared. And so what I'm going to do now is we're going to zoom in. I went ahead and downloaded the full resolution image, which I think is something like 15,000 pixels across. So yeah, so this is the full res image. And you can see that they actually imaged quite a lot more of the structure than what we saw in the Hubble image. And so let's go into one of those columns. So we're now looking at this tip. And again, we're seeing thousands of stars that have been revealed. So most of these stars were not visible in the Hubble image. And you see all these spectacular looking sort of landscape-like formations. And the way you can think about it is, again, imagining that there are powerful ultraviolet radiation and winds that's coming from those massive stars in this direction. And they're basically boiling up, photoionizing the cloud. And you can even see a sense of gas that's escaping, just boiling off. Along these sort of almost tendril-like structures. And there are still some regions of the cloud that's so dense that the mid-infrared can't penetrate. And so, remember what I said, it's likely that there are denser structures here that are protecting the rest of the cloud. Well, here's proof of that. We can't see through this in the mid-infrared, so that tells us this is a particularly dense part of the cloud. And notice that these stars are redder than the stars out here, and that's another clue that these stars are more embedded, they're more hidden by the gas and dust. It turns out that when starlight has to pass through a lot of gas and dust in interstellar space, it loses a lot of the blue light, and so the stars look red as a result. So let's go on to another part. Here's again yet another spectacular image zoomed in to look at one of the ends of those fingers. So again, this looks super dense because we can't see through it. But what's really cool is that you can see through this section here. So this looks just sort of phantom-like. It's very appropriate for Halloween because this is very ghostly looking. And then this reddish stuff is actually probably emission from. Actually, I haven't confirmed what the wavelengths are, but if I had to guess, this could be emission from either dust or from winds from young stars. So I'm not going to guess, but just lay those out as possible options. All right, here is the lower finger, and again we see a very dense knob that's protecting the rest of the cloud. And notice what I said earlier about the sort of gauze-like or ghostly parts of the cloud. You again see these very ghostly tendrils of gas all along here. It just makes it look really fantastic. Fantastically strange. And then this is part of the cloud that's much further to below where we were looking. So this is part of that base that wasn't visible in the Hubble image. And this, I think, again, without being able to confirm what the wavelengths are, I think what we're seeing is actually a very young embedded star. And young stars, in addition to accreting material, meaning pulling in gas gravitationally from the rest of the cloud, they can actually also eject gas via jets. And this is a normal part of the star formation process. And so I think what we're seeing is some of that jet material getting blown out from the star, and it's slamming into the surrounding molecular gas. And one other thing you might notice is that we see a lot of really bright stars have these strange-looking six-pointed lines, and those are unique to the James Webb Space Telescope. So these patterns are basically created by light going through the optical system of the telescope, and every telescope has a very unique pattern, and you can actually tell what telescope you observed with by looking at that pattern. And so bright point sources like stars, even in the best telescope, stars will appear as points. They will show this pattern, and so you'll see a lot of that tonight. All right, so let's go on to another nebula region, and we're going to talk about the Carina Nebula, and this is about 8,500 light years away, and this is Carina, but we're actually going to focus on sort of a side nebula off in this upper corner, and this what we're looking at here is about 2 degrees by 2 degrees across in the sky. And just to give you a sense of how big that is, you can basically fit about 16 full moons within this picture. So we've jumped to or zoomed in to that other nebula. It's called NGC 3324. And what we're going to do now is we're going to zoom in to even closer to this region right here. But what we're going to do is we're going to look at this region, but it's going to be turned around by 90 degrees. And so notice there's like a little knob that sticks out. Astronomers call these elephant trunks. And then there's a big bay. You can imagine this is like a sandy beach and the ocean's out here. And we're going to see that in this next image. And so there's that knob, here's that bay. And you can imagine the ocean and the beach. And this is an image taken from the Hubble Space Telescope. And again, this is the same sort of phenomena that we were talking about before. So in this case, there are massive stars in this nebula, and those massive stars are pumping out lots of ultraviolet photons, and they have these very powerful stellar winds, and they're basically etching away, they're eating away the shoreline, or they're eating away these gas clouds. And again, you can get a sense that the clouds are just boiling off as they're being photoevaporated. And now, now that we've been looking at this, let's look at what James Webb showed. So again, here is that knob, here's that bay, and like some of the other pictures, we're seeing more of the structure than we were before. And again, we're seeing many, many, many more stars than in the Hubble image. So again, proof that when you go into the infrared, you can peer through a lot of that muck that blocks visible starlight from coming through, and you again get these beautiful structures that appear because this is the process of erosion that's happening. The starlight and the stellar winds are eroding away this molecular cloud, and you're getting these beautiful structures. Now, what was fun, or at least for astronomers, is that this was released as to the public just a few months ago, but the data was also made available to professional astronomers, and a paper came out just after these astronomers, I'm sure, spent a lot of days and nights just going through the data in order to describe some of the things that they see in this image. So this image was, anyone could have gone and studied the image to write a paper, but they were the ones who got the first one out. And what they were able to do was they were able to identify dozens and dozens of structures that are tied to young stars. And so this is a map, again, that elephant trunk with that bay, and looking in the mid-infrared, again, you can get a sense of seeing a lot more than what was visible. And this is a zoomed-in part to this right here. And we'll be seeing what this is right here. So what we're seeing is a young star. Remember what I said, very young stars, in addition to accreting material that's fallen in due to gravity, that material falls into and jams up in an accretion disk, so the gas slowly spirals in. But as it spirals in, it actually gets jammed up by magnetic fields. And so a lot of the material can actually get expelled out in jets. And you can actually get a sense of these jets right here, where you have these bow shocks here and here. And then there's also a counterjet on the other side. So this is what astronomers call a bipolar outflow, meaning it's coming out in the polar directions. You can imagine like a north and south direction. And there's even another outflow, you can get a sense, coming out from this direction here. And this is kind of hard to see when you've combined the different colors. And so what astronomers like to do is like to focus on one color at a time. And they can also, using the different images and data that were taken by James Webb, they can actually subtract out the starlight and subtract out a lot of the other light that's confusing the situation. So that's what this image on the left is, where they've subtracted out what they call the continuum emission. And so you can sort of see that these three stars, the subtraction isn't perfect, but that's why they have this very funny looking shapes. They correspond to these three stars here. And when you subtract out the continuum emission, the hydrogen emission that's responsible for these bow shocks shows up really nicely in this negative image. And then they also identify these hydrogen emission knots as coming from another jet. So, and then they've identified 31 different outflows from different young stars in this region. And so these outflows, we only see them when those jets and the winds from these stars impact or shock the surrounding gas. And so this paper is basically trying to identify all the different places where they see shocked emission, and they're trying to figure out where all these young stars are. And so I'm just showing just some more examples of this, but it just shows you how dense these emission knots can be. And it turns out that this isn't unusual. Whenever we look in star-forming regions, we tend to find lots and lots of stars all forming in the same place and all forming at once. So stars forming individually is actually kind of rare in our galaxy and in other galaxies. All right, let's go on to yet another kind of amazing looking image that was released this past month. And this is WR140. And WR stands for Wolf-Rayet. And Wolf-Rayet stars are massive stars that tend to be much more massive than our sun, so about 8 to 10 times, if not more. And in this case, this particular star has some really odd-looking ring structures surrounding it. And I think and this star has actually been studied for quite a while, but not in as much detail as what we see from James Webb. But when this was first released, there was a lot of internet chatter about whether this was caused by aliens or whether there's something else really strange going on in the sky. But it turns out that astronomers have a pretty good idea of what's going on. And that's because there isn't just one star here, there are actually two stars. And so there's a paper that was released just this past month by Ryan Lau and a bunch of collaborators that talked about the new James Webb observations. And basically what is going on is that there are two massive stars. So one, the Wolf-Rayet star, is about 10 times the mass of our sun. And here is our sun shown to scale compared to how big the Wolf-Rayet star is. And there's another massive star, what we call an O star, that is about 30 times the mass of our sun. And so what's happening is these two stars are in orbit around each other, or they're in orbit around a common center of gravity. And the orbit of the Wolf-Rayet star is pretty elliptical. And so what that means is that every time it passes by the other star, let's watch that animation again, it causes the other star to expel part of its outer envelope or its atmosphere out as a wind-like structure. So this is just due to the tidal forces, the gravity of one star acting on the next one. And in the effect, and this is an animation from another paper that came out earlier this year. It's basically, and this is a computer model, but you can see how, because of the geometry of the two stars, you can actually get structures when viewed from the direction of the sun. It can give you structures that look like what we're seeing in the images taken, or the image taken from the James Webb Space Telescope. So it's really wonderful that we're able to get as much detail as we can, just because I think prior to James Webb, the amount of resolution that we could get on the system, you might be able to see maybe 2 rings, and here we see, on the order of 7 or more. Actually, you can see that there are a lot of fainter rings coming out. So we get a wonderful image from James Webb, and we also get great computer simulations that show us how the system is actually working physics-wise, and how these winds are being ejected from that stellar pair. And let's go ahead and go on ahead. All right, so for this next story, we're going to stop talking about James Webb, and we're going to switch gears and talk about planets that orbit around other stars. So since in the last actually 27 years now, astronomers have discovered more than 5,000 planets orbiting other stars. So in our solar system, we have, depending on how you count planets and dwarf planets, we have on the order of 10 or 20 known planets and dwarf planets. And that's absolutely swamped by the number of planets that we know outside of our solar system. And what's one of the interesting discoveries when you have so many planets that are discovered is that you can start trying to figure out properties of all of these planets as a group. And so what we're seeing are what are known as histograms. And what they're doing is they're plotting the number of planets that we see by a certain size. So here is this number here corresponds to the number of Earth-sized planets. So planets equal to Earth's diameter. And this here corresponds to a planet that's 6 times Earth's diameter. This is 10 times Earth's diameter, and so on. And so what we're seeing is that if you count up the number of Earth-like planets, so planets that are the same size as Earth, you might get around 50, 60 planets in this particular survey. But if you look at planets that are slightly larger than the Earth, say maybe 1.5 times the size of the Earth, you actually get quite a lot more. And you also get a lot more when you look at planets that are maybe twice the size of the Earth. And then you get fewer and fewer planets, Earth-like planets, as you get to larger and larger radii. And these are for all what we call small planets. So these are not Jupiter-sized planets, not gas giants, but these are more Earth-like. But what's really interesting, and this is noticed just 5 years ago, is there seems to be a valley or a gap. So right around 1.8 times the radius or the diameter of the Earth, there seems to be a deficit of worlds that's of this size. And it doesn't matter how you break up the distribution. You often, this gap might be smaller or larger, but that gap seems to always to be there. And there are some people have been puzzling about what the cause of this gap is. It probably has to do with how planets are formed in solar systems. And so a possible answer came with a paper that came out this past month from a pair of astronomers from Spain. And what they have done is they have looked at the observational evidence for planets that exist, and there are and this is actually very hard to do, but you can figure out how big a planet is. So that's what the radius is here. But you can also, through some very tricky measurements, figure out how massive the planet is, how big they are, and or how much they weigh effectively. And so when they went through the data that they had out of thousands and thousands of planets, they had 40 plus worlds that they had good enough data for their sizes, for their diameters or their radius, and they also had good data for how heavy or massive they were. And so what they did was they plotted the two variables. And here is the Earth in comparison. So that green cross with the circle around it, that represents the Earth. So we're looking at one Earth mass and one Earth radius. And then so all these other planets are relative to how much bigger or smaller they are compared to the Earth. And what they see are a bunch of worlds that fall along this line, and these are the Earth-like worlds. And if you think about the Earth is mostly rocky, and we have a very thin atmosphere compared to the size of the planet. The atmosphere's maybe, depending on how you define it, perhaps no more than 50, 60 miles thick compared to the thousands of miles associated with the diameter of the Earth. And the Earth also has some water, but not very much water at all. I mean, the oceans, again, you can sort of think of as just a very thin layer on top of the Earth. Now compare that. So if you create models for Earth-like worlds, they would actually fall along this line. So all these worlds are, in a sense, Earth-like, meaning they are mostly rocky, and if they do have water, there's not very much water. Now, in comparison, there are a bunch of what are called water worlds. And these are worlds that have approximately 50% water and 50% rock. And they tend to fall along this line here. And then there's another set of worlds that don't fall on either of those lines. And those are what we call the puffy planets. And these planets have hydrogen and helium atmospheres. And we think that heating from the star in their system tends to puff out those atmospheres, and it causes the sizes of the planets to be much bigger. So you have sizes that are 2.5 to 3.5 times that of the Earth, even though they're not that much more massive. I mean, they're on the order of 10 to 20 times more massive. And what we see is you actually see the small planet valley that we pointed out earlier. So note that gap from here corresponds to right about here, and this gap shows up because there aren't that many small water worlds, and you're also running low on big rocky planets. And so whereas most of the rocky planets are here, and then most of the water worlds are up there, and so as a result, this gap kind of naturally shows up in the data. And then the other thing that they figured out, that they realized, is that there are really no planets, or very few planets, that are in between the half water, half rocky worlds and the rocky planets. So that is a really interesting observation if you think about it. And it turns out that this was predicted by people running computer simulations. And this has to do with the fact that there are a couple of different theories as to how planets grow. And one of them is called planetesimal accretion. And the idea behind this is that planets grow when these planetesimal cores, and let's watch that animation again. These are bodies that might be 100 kilometers across, so not totally planet-sized, but they're still pretty big. But they can collide and merge to form larger and larger planets. So that's one model for how planets can grow. The other is called pebble accretion. And the idea is that instead of having large things hit each other and growing, you have much smaller things. So pebbles that are perhaps just centimeters across instead of hundreds of kilometers. And those that's another way of growing planets. And so there's been a lot of debate about which of these methods actually results in planet formation. And another aspect of planet formation that we have to talk about is there's also something known as the snow line. And so if you think about a young solar system, there's a star at the center. You can imagine the sun early in our solar system's history. And there's also a lot of material that's in orbit around the star. And depending on how far away it is in orbit, it will be warmed by the starlight coming from that central star. But at a certain point, because as you're getting further and further away, the strength of that starlight, the amount of heating, drops. And at a certain point, you reach what's known as the snow line. And what that means is that past this point, the water and other volatile compounds like ammonia and methane, they can actually start freezing out. And so as you get further and further out here, you'll start seeing not just rocky material, but you'll start seeing a lot of ices as a result. And so it turns out that the material that builds planets in here tends to be all rocky. There isn't very much in the way of water or ices, just because this region is too warm for water to solidify into ice and for it to stick to the material that's going to form planets. It just stays in a gas form. But the material out here, it's cold enough for the ices to be embedded in this material. And it turns out that when people do simulations, this material is on the order of about 1-to-1 ratio for snow or ice to rock. And so what that means is that if you are finding planets that have that 50% ice to 50% rock ratio, it's likely to form from material out here. And then it turns out that when people do computer simulations, and this is a paper from last year, they can actually get features that are similar to what we just saw in that other plot. So again, this is plotting the mass of the planet versus its size. And again, we see two different lines, one corresponding to very dry planets. So this green color corresponds to almost no water or no ice. And these dark blue or purple colors corresponds to roughly about half ice fraction. So these simulations actually show very similar types of plots as we had saw previously in the actual observations. And so if you're trying to explain planet formation, whether it's from planetesimals, these giant 100-kilometer size embryos, planetary embryos crashing into each other, or whether it's smaller, inch or centimeter sized pebbles that are attaching to each other as they orbit, it turns out that at least in this particular paper, the planetesimal model doesn't work, and it only works for pebbles. And that's just because in the planetesimal model, you can actually get material that's in between half ice and half rock. So you should be able to get a spread of different values for the rock and ice, but it's in the pebble accretion where you can get material that's exactly half rock and half ice. And so it looks like, at least for the stars that they're looking at, the pebble accretion model describes how these planets were built better than the planetesimal model. All right, so we're going to end our last story to talk about the DART mission. This is the Double Asteroid Redirection Test. And this was an event that you might have heard about last month on September 26th. This NASA space probe crashed into a small asteroid in order to change its orbit. And this was our first attempt to alter an orbit of an asteroid in order to potentially deflect future dangerous asteroids in case we find an asteroid that's in danger of hitting the Earth. And so what the DART mission did was it was sent to this binary asteroid pair. So the main asteroid is called Didymos, and in orbit around it is a much smaller asteroid, or about half the size, called Dimorphos. And the idea is to change to slam the DART spacecraft into Dimorphos and change its orbit into a smaller orbit, and which would orbit faster around. And in addition to DART, there was also a small CubeSat, meaning just a small satellite that was attached to DART before it was released, a Lycia cube. And this is built by the Italian Space Agency. And as DART smashed into or impacted Dimorphos, this Lycia cube was used to image or to see, to take additional images and to see how it all went. And this is an image taken from the DART spacecraft. And here are some additional images as the DART spacecraft closed in to the surface. And what we see is instead of one sort of big rock, Dimorphos actually looks like a big pile of rubble. It looks like a bunch of boulders and random fragments of rock that are all loosely gravitationally bound together, because the closer you get, the more rocky, and it just looks like a bunch of loose gravel that you might find in somebody's yard. And then here is the last image that was sent back before the transmission was cut off by the collision. And then here is an animation showing what that close approach looked like from the DART spacecraft. So here is the larger asteroid, Didymos, and we're approaching Dimorphos. And bam, we hit the surface. Let's look at it again. And this is broadcast live on NASA, so people were able to see this in real time as it happened, at the same time as the scientists and the mission control people. So that's a pretty amazing thing technologically, if you think about it. Now, NASA released all these images, and what happened as a result was that people took advantage of the image release, and they created their own versions of the image. So this is someone taking all the different images sent back from DART, and then combining them together to create a what they call a high-res version of Dimorphos. And then this other set of image created by a guy on Twitter, JP Major, he actually took these images and sent them to an artificial intelligence processing software to basically process the images to make them look even more high res than they were. So if we look at, let's see, here is the NASA version. And then I think, here we go. So here is his version versus the NASA version. So you can see that whatever software he used was able to put out more detail, although whether the scientists would actually be able to use this is uncertain, because I'm not sure the scientists would trust some AI program that they don't quite understand how it works to create detail for them where it doesn't exist. So that's pretty cool that people are doing this. But in addition to these close-up images sent back from the DART spacecraft, we also had images taken by telescopes on the ground as well as in space. So here are the Hubble Space Telescope images, as well as the James Webb image. And it turns out that Hubble, the team that took the Hubble images, had something like 45 of them planned, and the Webb team had 10 images that they took. So we're only seeing a small fraction of what was imaged by the two telescopes. And I'm sure in the future, when the papers are written and future press releases come out, you'll see even more images than what we're seeing here. But this is taken about 8 hours after the collision, and the Webb image was taken about 4 hours after. And again, we notice that hexagonal, the 6 spike pattern. That's from the optics on the Webb Space Telescope. So again, this is due to the fact that we have a very bright point source, and so these diffraction spikes are not real, in the sense that we're not seeing material coming out as 6 points or 6 lines. That's just part of the optics. And similarly, Hubble has a 4 point diffraction pattern. So you kind of have to ignore this cross shape from Hubble, because that's part of Hubble's optical system that causes that pattern. So here is a sequence of images from Hubble. So first one, 22 minutes after the impact, and the next one, 5 hours, and then 8 hours later. And what's really remarkable, I don't know if we can turn off the lights. It's kind of bright, but you can sort of get a sense that there's stuff that's pouring out of the asteroid that we can't see in this image, and you can sort of get a sense that it's sort of curling out. Oh yeah, thank you very much, Charlotte. And what's also really interesting, and I'm sure people are really analyzing and studying this, is that the brightness of the impact hasn't decreased at all after 8 hours. So something is definitely glowing red hot or in the impact zone, and this asteroid became about 3 times brighter as a result. Now, what they and then here is yet another image, and this is actually taken from the Italian CubeSat. And what they did was they changed the contrast in successive boxes as you get further and further out. So it's super bright in the center, and it's very faint out here. And by playing around with the contrast and the brightness levels, they can get a lot more detail in the center, and then you can again see progressively more detail as you come out, as the features become fainter. So again, you have the spectacular stuff that's pouring off ejecta that was blown out from the impact, and there's material that's sort of curling out, and I'm sure the teams of researchers are working on figuring out exactly what properties in the asteroid and how the impactor might have caused the features that we're seeing in the ejecta. Now, it turns out that the impactor, the DART mission was successful in changing the orbit, and it actually shortened the orbit by about half an hour. But how do we know that the orbit was changed? Because this asteroid pair is so far away that it's really hard. You can't actually separate out the smaller asteroid from the larger asteroid in telescope images, and so it would be very difficult to figure out how the orbit changed. But what they did was they analyzed something called the light curve. And so as the smaller asteroid orbited, Dimorphos orbited around Didymus, it would go into Didymos's shadow in part of its orbit, and it would also cast a shadow on Didymus. So watch right here. You can see the shadow of the smaller asteroid being cast on the larger asteroid. And each time the smaller asteroid shadow appeared, you had a small dip in the light, and each time it went into Didymos's shadow, you had a larger dip in the light. And so by basically timing and observing the light and timing when these dips occurred, you can figure out what the orbital period was. So basically how long it takes to go around once. And this is the data that they got. And so what we're seeing is the gray bars represent the old orbit. So the old orbit would correspond to these gray arrows, and the new orbit, which is half an hour shorter. So the previous orbit was almost 12 hours, 11 hours 55 minutes. The new orbit is 11 hours and 23 minutes. And what they see is that with the new orbit, those features that we see in the light curve get progressively further off. They're no longer synchronized with the previous orbit. And so that's what this is showing. And then in addition, they're able to also look at this asteroid pair using radio telescopes that can use radar to basically determine the positions of the main asteroid and then the satellite asteroid. And boy, it's actually hard to see these colors because they're so dim, but I think this is like a faintly blue spot. This is what the original position was supposed to be, and this is what the new position is after the orbit's been changed. And this is very pixelated, but this is another confirmation with really good radio telescopes to show how the orbit has changed. So with that, I think we'll go ahead and switch to a Q&A. And if we can get the lights back on down at the bottom, I'll be happy to answer people's questions.